Good afternoon, ladies and gentlemen, and thank you, George and Zoe, for hosting this seminar and for this opportunity to talk to you all today. As George mentioned, I'm going to give an overview of how important batteries are in the sustainable electrification and all the possible opportunities that may unfold in the coming years. This particular introduction to this topic of mine is I got sort of three areas here. The central part we can see related to electrification of transportation, for example, and road transportation, aviation, marine and industrial activities, and like such as traction, for example. And what is required here is by about 2030, the end of this decade, one would like the batteries to have a certain energy density, it's about 400 watt-hour per kilogram, and volumetric density of 750 watt-hour per liter, and at least 2,000 cycles at 80% left of discharge, and the price tag of about $100 US dollars per kilowatt hour, with 12 minutes of charging time, and safe and recyclable and possibly used for second life in other applications, which may not be as demanding as transportation and industrial applications. The other area on the left is energy storage with respect to renewable energy systems. So battery is one great opportunity to be able to use those renewable energy systems, especially with those that are of intermittent nature. And here the target cycle costs must be very, very low, 5 cents per kilowatt hour per cycle, and should have much larger cycle. In fact, it should be able to last as long as one of those renewable energy systems. And the last one on the right-hand side is to have some kind of hybrid system. It may be smart grid, small independent grid systems. It's such that we have vehicle can actually feed in electricity or receive electricity from the same system. Next slide. Okay, so the energy from renewable sources, I think I'm sure that is all very, very familiar to all of us, but just to introduce, of course, when we have a solar photovoltaic cells with batteries, wind energy with batteries, solid oxide fuels using biogas and green hydrogen and green ammonia, biodiesel generators, biogas generators, micro hydro and hybrid system. And energy storage is the weakest, but actually it's an important, crucial link. And with economy of scale and decreasing costs, can easily be the game changer in the next decades to come. The competing energy storage technologies, I think I'm just going to focus mainly on batteries here. There's a whole list of battery chemistries under considerations, and advanced lead acid batteries already are used quite widely, especially when cost is an important factor. But life is an issue with these batteries at the moment. And lithium batteries, they actually are already being deployed in this area. And there's a whole range of other batteries in the development with sodium, potassium, sulfur-based cathodes, magnesium, etc. And not only even cheaper, more common element like zinc, aluminum. And I use lithium here because, again, they can be used as a semi-fuel cell with oxygen or air as an oxidant. And they could be in aqueous systems, polymeric, molten salt, and solid oxide systems. And flow batteries are seen as important development. It's a large number of projects and trials and commercial availability of flow batteries and redox batteries. And these are especially for renewable energy storage systems in large scale systems. And if you have a look at the energy and power sector investment, global investment in this area at the moment, it's about 75% of it, according to various sources, is attracted by renewable energy storage systems. And decline in other areas relatively or stagnant. Not the amount that is probably remain the same, but I think the bulk of the new investment is going into renewable energy sources. Of course, zero carbon is a driving force, and there are tremendous real and immediate benefits in cleaning up air and water inland just by changing the transportation, for example, from IC engines to electrical vehicles. Okay. I think here, this particular graph that I've shown here, it's actually emphasizes on x-axis, the power ratings and the discharge time related to that particular power device. And supercapacitor, we know is extremely fast in seconds, but it's a low power. And the flow batteries is on the higher side. And the sodium sulfur is looking pretty good. It's also applied in some other places already, but it's not cheap, it's not a low cost option. Okay. And how the batteries can be divided in many different ways. Chemistry is one way, but another method by which it's worth looking at is that if all the ingredients are enclosed and sealed in a system, in the active materials, and of course it can be cycled many times as a secondary also rechargeable batteries, but after a certain time the capacity decreases continuously. Yeah. So and here the energy and power highly linked with each other, linked together. Or you can have this kind of a semi-solid or organic or inorganic redox flow system where the power and energy of the system are delinked. And here, because you have a system of electrolytes which are pumped, there's one for the cathode side, other for the anode side, and therefore the capacity and energy density depends on that amount of storage at the reservoir. And of course, the surface area, therefore the stack is also important. Yeah. And when air is used, or even carbon dioxide in the future, is used as one of our electrode, an electroactive material, then it takes the form of a semi-fuel cell. So, for example, lithium air batteries are extremely high energy densities. Yeah, but they are probably take another decade or more before they become possible, practical. And zinc bromine is a kind of a redox battery. It's a hybrid kind of a system, and it's this redox with vanadium and zinc batteries, bromine batteries have been around for a while, but they are undergoing rapid development at this stage and applications. And in batteries, when the system is completely enclosed and the active materials are cycling from one electrode to the other, the specific energy in terms of gravimetric and the specific power, again gravimetric power, see that when the power increases, energy density decreases. So therefore there is a trade-off. Of course, one will, and the capacitors are extremely high power rating, but the specific energy is very low. So in a way, the search is for continuously moving in this direction where the ideal energy storage will have good power, specific power, and good specific energy. And the redox battery, flow batteries for grid storage, such as the vanadium system, where you can see that what is known as a catholyte and anolyte with a reservoir of, in this case, it could be aqueous system, or it could be aqueous system containing organic molecules. Here there's a vanadium inorganic molecules, and they are pumped continuously through, in one case, the cathode element, other case, the anode element. Of course, as with time, as the redox reaction proceeds, one may have to charge it back again. Yeah, so they reverse the reactions to restore the energy as it was before. Yeah, and the reactions in this case, the oxidation state change for the vanadium can change from +2 all the way to +4, +2 to +5. So therefore, with using one single chemistry of vanadium, one can get both the electrode reactions at the cathode and the anode. Okay. Yeah, so some very general note for those who may want to look at the thinking behind the different chemistries and how they do evolve with time, because in addition to the very popular lithium-ion batteries, there are many other opportunities and many other options that are being developed for various reasons. Cost may be one reason, supply chain may be another, and combination of energy and power, etc. So if I look at these various values like potential charge, current, the valency of the electroactive element, and the Faraday constant and molecular weight, these are the only information we require to understand the concepts. So for energy and power optimization, we actually optimizing or maximizing potential times charge or potential times current. And this is the target. It's very, very high for most applications. And we also want to maximize their lifetime, the cycle life. So therefore, it can be done for several cycles and over a long period of time. And that's a difficult ask some cases. Yeah. And high voltage requires high cathode electropotentials. Yeah. And also it requires very low, ideally zero anode potential. And when the potential difference is very large, there's a pressure on the stability of the electrolyte. So therefore, the choice of electrolyte has to meet that has to remain stable as well throughout the process. In order to maximize the gravimetric capacity, often quoted milliamp hour per gram or amp hour per kilogram, the Faraday's law is a starting point. It's really as given here. Is actually the two quantities we have control over, Z and the molecular weight. And of course, we may want to maximize the volumetric capacity in terms of liter, centimeter cube. Then you want dense electrodes. For example, magnesium is better than lithium for this purpose. Just looking at the anode. Yeah. So now, again, using the charge and the molecular weight, and what I have here ordered these elements in increasing molecular weight divided by Z. So obviously, if we could get solid hydrogen or in a host, that of course will have the highest energy density. But that's not easy to achieve because some of the materials in which you can hold hydrogen and then use as a battery are themselves very dense, so you lose that advantage. So that's the reason why lithium is extremely popular. Yes, that ratio is about 7, so it stands as the best solid anode possible. Aluminum is not far off. It's 27 divided by 3 is 9. So aluminum actually potentially is very good, but of course we know it forms a very, very passive aluminum oxide layer. But nevertheless, that can still be depassivated, and it's quite popular research, and there are some products available in the market for trials. Magnesium is also very attractive. It's 12 is the number for it. Yeah, and there's, I think there's a good potential for this, and it's available in tonnage quantities. Sodium is actually become quite recently quite popular, and because it can actually replace or use the existing lithium assembly line without any problem. And it is much cheaper, and its supply chain constraints are minimal because it's available from everywhere. Potassium, again, similar to sodium. Okay. And then, of course, there's a whole list there that we know that zinc, nickel, silver, lead, they're already used. But rare earth is kind of a hugely stable. Cathodes can form a reaction with rare earth. So they can be some very, very heavy batteries, can be attractive. Alloys such as hydrogen, lithium, now this is a combination of elements. And there's a lot of work going on because there's no reason why it must be restricted to one ion. Combination of ions is an interesting possibility. Okay. And of course, when they're nanostructure, one can maximize the loading of hydrogen. Both elements can participate in discharge. Or it could be a combination of lithium and aluminum, sodium, and so on. So these are opportunities. These are new chemistries evolving out of the existing chemistries. Of course, the question usually arises as soon as you do research on this, the mixed discharging components, what does determine the electropotential? Yeah, so there's a whole range of potential that arise at different discharge time. Okay. Now, anode components which act as a host are not discharged. They are basically passive, and they are important for safety or for holding the material, but they add weight. Say, for example, carbon or oxides that are used in lithium-ion batteries, a good example. That's why the concept of anode weight factor is a multiplier, or one may say divider, which actually reduces the capacity by the amount it's multiplied by, yeah, per gram, let's say, of the anode. So take a lithium-ion battery. Yeah, lithium itself has a capacity of 3,860 milliamp hour per gram. Yeah, and that is a theoretical capacity. But as soon as we use carbon, the multiplier is less than 0.1. It reduces to 372 milliamp hour. Yeah, but keeps the battery safe. So therefore, it will be very attractive. Somehow we find safe way of using lithium. Needless to say, a tremendous amount of work is going on to do that at the moment. Okay. For a cathode, we can't avoid a reactive host because essentially it is a material which stabilizes the electroactive material to a very stable phase. The more stable it is, the higher is the potential available from that cell. And the cathode factor, weight factor, FC, will always be considerably less than 1. We do not want it to be too low, but take typical cobalt oxide cathode in the lithium-ion battery that's used on a mobile phone or a laptop. This factor is 0.04. Yeah, so just for the lithium capacity is massive, but cobalt oxide molecular weight is quite high. So that determines energy density for that cathode. Oxygen gas is nearly a zero weight option, of course. Yeah, but by itself, it's not enough to sustain the reaction because it requires supporting electrocatalysts. It requires a conducting material. Yeah, and it may also become the host for any product that may form from the reaction. Yeah. But nevertheless, the multiplying factor of 0.5 may be possible to achieve in the future. It makes this, for example, with respect to lithium or sodium or zinc even, an air electrode, oxygen electrode is very, very attractive for future. And all we know, a lot of things we have learned in electrocatalysis for fuel cells could be applied here. Sulfur is a very good candidate. It's a very low cost material. It's available in large quantities. It's also available from desulfurizing of oil and gas in large quantities, in addition to natural sulfur. It's got a very low molecular weight, and Z is 2. So FCF up to 0.2 is possible. So I think sulfur-based cathode is very attractive candidate in the evolving chemistry. And of course, sodium sulfur batteries already exist commercially. The lithium sulfur battery is a possible next development that may take place. Okay, and other lighter molecular weights are organic materials which can incorporate hydrogen and lithium. Other M can also be considered important. So what we're looking here is a very low thermodynamic activity of the electroactive species to obtain a high cathode potential. And that's then, and at those kind of potentials, electrolyte can readily be decomposed. So therefore, a search for a proper electrolyte becomes a very important part of the research. And fluorides are more, there are other opportunities that may use CO2 as the cathode gas instead of air. So therefore, I can start using some of the CO2 that we produce as actually a material for generating energy. Briefly on electrolytes, the categories are such as aqueous liquid solution with salts or acids or bases, organic solvents, like lithium-ion batteries use solid electrolytes. This is an important development for safety of batteries in the future, especially for lithium-ion batteries. Ionic liquids is an active area of research. It may allow us to extend the stability of electrolytes and therefore go for extremely high potential in batteries as one option. Okay. And it must satisfy a number of properties as mentioned here. Composites and solid electrolytes are actually developing very, very fast for safe lithium-ion batteries. Okay, so just to give a cartoon of a lithium-ion battery, and it uses copper as a current collector for the negative electrode, and uses aluminum as a current collector for the cathode, the positive electrode. And it cycles to intercalate the lithium from one stuck host to the other host. and it can be discharged and charged many, many times, as we know. And the nominal potential is about 4.2. And the anode is basically carbon. It's a graphite, and it can actually intercalate lithium, for example. Our cathode is again materials such as lithium cobalt oxide, lithium nickel oxide, manganese, the spinel, or combination of nickel, cobalt, and manganese, or nickel, cobalt, and aluminum. Yeah, sometimes known as NCA. And LFP is the lithium iron phosphate. So these are the possible cathodes, and all are being used or developed rapidly. I think it's about 12 to maybe 13 years ago, and it started the process. Tesla actually in some sense changed the game by introducing this extremely expensive cars, but with a large number of batteries all put together, using the existing sort of available batteries and the 18650 cells with the Panasonic cells, with the nickel, cobalt, aluminum as the cathode, and graphite as the anode. And this is compared to 1995, when the price of a lithium-ion battery would have been about $3,000 per kilowatt hour. The price at 12 years ago had come down to $200 per kilowatt hour. It's even lower now today, and very soon is approaching the $100 per kilowatt hour mark. And the metrics that the Tesla car used are shown here. And the pack cost was estimated to be about $17,000. And most of the cost of the battery is actually the materials in it, especially because it uses cobalt. It's quite expensive. Yeah, and the range, the initial range was around 200 miles and 1,000 cycles. It really changed the game quite rapidly after that. And the charging time of about 30 minutes. Right. So yeah, so if we look at the cathode, lithium cobalt oxide is the mainstay of all the current lithium-ion batteries. Yeah, it's got good capacity. Yeah, it's got a number of good properties, but it does capacity fade at high rates. So therefore, it's not very suitable for electrification of transportation. And that's one of the reasons why Tesla chose NCA, for example. It's got a good capacity, and it's got good cycling. It's moderate costs because the cobalt amount is lower now. However, it has got one problem. High temperature is a serious capacity fade. So therefore, it cannot be used in many parts of the world, especially in hot weather. And that happens because the nickel cation disorders. So there's this, and in other words, lithium can go into the nickel sites. So there are safety issues from that. Yeah. For safety, lithium iron phosphate is the best. It doesn't use any cobalt, so potentially it's made of materials which are available readily. It is relatively low cost. It's got a very low self-discharge. It can be cycled many, many times. It has got low potential. As a result of that, the calculated energy, theoretical energy is lower than all the other batteries that we're talking about with lithium. However, it can use the full potential range available. So in fact, if that point is taken into account, it's actually surprisingly good. Yeah, so therefore, it's not surprising there are lots of cars available with LFP at the moment. But the future generation, and there's definitely the target in the UK and Europe and many other places and US, is actually decreasing the cobalt content. Yeah, cobalt is an extremely good catalyst in the batteries. It really does help. So, but to decrease the content to the lowest possible level, so we're evolving in the direction such that the first number is for nickel, manganese, and cobalt. The ratio of cobalt to other two elements is to be decreased rapidly in the coming years. Okay, and on the anode materials, the graphite, natural or synthetic, they're both used. And hard carbon has also been used, although it's discontinued for lithium-ion batteries. In fact, but it is the one that may sustain sodium-ion batteries, because the sodium cannot be intercalated to graphite without breaking it easily. But hard carbon also has a graphitic, not only the graphitic region, similar to graphite storage mechanism, but it also has microporous regions, microvoids with extremely high capacity. So it's much higher than what you might calculate as a theoretical capacity for graphite. And is the only way forward as a host in the carbon chemistry for sodium. Silicon has very high capacity. It's low cost, but it suffers such a large volume change when it reacts with lithium that it rapidly, the capacity fades away. So its battery is not stable for long periods of time. But however, carbon silicon, so increasing amount of silicon, starting from few percent, and is already increased to quite a considerable percentage, 5 to 10% in e-batteries. That improves the performance. So you use combination of carbon and silicon, two different mechanisms simultaneously. Niobites are very safe. They're good for fast charging, more reliable. They're also suitable for sodium-ion batteries, but they offer lower battery potential and therefore low energy. But nevertheless, this may have many, many applications, especially for the fast charging applications. Okay, pure lithium, and that is the holy grail of lithium-ion batteries. If that can be used, the capacity will jump very high. But given the high potential in the battery, the safety risks are high. Even with lithium carbon in the host, we know that the accidents that take place, especially in vehicles. So this may be a very important issue to solve. But there's extensive research to make the lithium safer by various kinds of interlayers and coatings, etc. Okay. So the research and innovation targets, starting from the current existing system that I already described, is that this was predicted in 2019. So we are already doing quite a lot of work going on in the higher NCM, next generation, and silicon carbon, and what is known as a conversion material, lithium-sulfur, and all solid state, and lithium air or lithium oxygen. So we can see the direction of travel that is expected over the next 10 years, not merely that there'll be lots of batteries from the current accepted and well-advanced technologies, but new chemistries and new modifications will arise in that mix. Is just a map which shows the energy density in terms of volume and therefore the size, energy density in terms of the weight, and therefore how heavy it is. And if you look at lead acid in 1858, and still one of the most popular batteries because of its low cost and being able to drive in tractions and starting and lighting and ignition of cars. And then we had nickel cadmium, which dominated, many of the markets higher because of its higher energy for nearly a century before nickel metal hydride arrived. And nickel metal hydride had advantage that the existing nickel cadmium assembly line could be used. Yes, so therefore it became quite popular, except that the lithium-ion battery arose very quickly. It even higher energy densities. So therefore, it offered tremendous competition to nickel metal hydride and sort of put it into the second place straight away. And the lithium polymer, which is really another version of lithium-ion batteries, not a true, it's a soft polymer, soft gel material. It became popular as well. And then the future, we're looking at lithium-sulfur with potentially very high performance, but there are many problems to solve. And lithium ion is outside this chart. It's actually a semi-fuel cell. Yeah. And the intention or the forecasts are from 180 gigawatt hour. In 2030, we could be looking at 2000 gigawatt hour, which is about well over 3/4 in electrical vehicles. So that's what's going to drive it. And practically speaking, the battery devices are very, very simple to look at. It's got an aluminum and copper foil as current collectors, and a cathode active material, and a polymer electrolyte or a separator filled with liquid electrolyte, and an anode active material. And the assembly line is well developed now, and they have to be in very dry conditions, controlled clean rooms. So therefore, for large scale production, they're quite expensive capital costs. All the machineries are readily available from many sources, and any new battery chemistry that comes up, if it's able to use the existing known technology and assembly line, it will actually fast track its development. Okay. I'm going to say something about lithium-sulfur battery as an area of very intense research, and it can actually be provide opportunities in market that do not exist at the moment, because energy density is 4 times that of lithium-ion battery. Can it be lighter and safer? And yeah, so okay, some of the applications are mentioned here. Yeah, so if you look at the theoretical value of lithium-sulfur battery, 2,500 watt-hour per kilogram. So all we need to be able to use is 1/4 of that energy. It will already be better than lithium-ion battery. And similarly for half of the volumetric energy density. Yeah. But okay, if we look at this, chemistry is very complex. It's not as simple. It looks very simple, lithium and sulfur, but sulfur is a crown molecule, and once it begins to dissolve in the organic solvent containing the lithium salt as electrolyte, and it forms various polysulfides. They are polymeric in nature. They make the electrolyte quite viscous, and then the potential decreases, and then it reaches a sort of a steady state where other polysulfides form, higher lithium content, and ultimately it forms Li2S2 and Li2S. These are not soluble or less soluble in the solvent, and they precipitate out. Both sulfur S8 and Li2S are highly insulating solids. So that's one problem. Yeah. So, but however, if all that energy could be used, and then it has got a very, very high capacity. And even this is a picture of the possible application in the future, and the price, I think it still is valid even after 10 years. Okay. So what are the problems with the lithium sulfur batteries? Yeah, solid sulfur cathode, insulating nature of sulfur and the lithium sulfide, very high solubility and diffusivity of intermediate polysulfides. Volume expansion between the cycling is very, very large, or expansion or contraction, and the speciation is another issue. And because this uses pure lithium metal, so this, of course, is a tremendous learning curve here for able to use pure lithium. But this battery produces only 2.1 volts. So therefore, it's relatively lithium can be seen this. And also that there's a reaction that takes place between lithium metal and the polysulfide, which is soluble in the electrolyte. So it's continuously polishing the dendrite. Yeah. But however, at high charge rate, you might find the dendrite form uncontrollably. Okay, and the separator actually is a large loss of lithium sulfide. But there's an uncontrolled lithium sulfur diffusion and the chemical gradient, and therefore it shuttles from one end to the other. So to solve the problem, there are many approaches. One is the trade-off between the capacity and the cycle stability. So therefore, when we get a very high capacity, cycle life is very low, and vice versa. So there are some of the approaches are to somehow slow down or not fully stop the shuttling of the polysulfide from one electrode to the other, but slowing down, keep it at a level where there's not too much of that loss. And it's basically a parasitic reaction, a parasitic movement, a chemical movement of the polysulfide is actually represented as a huge loss of capacity with time. And use of 2D catalysis is a huge opportunity that some of the 2D materials that are being developed, they perhaps can act as a very good catalyst for so that the chemical reactions, the chemical diffusion is slower, time constant than the electrochemical reaction, for example. Yeah. And that such a material can have very high surface area and have a porous surface. Yeah. So the number of opportunities here, and this is a growing area of research as well. And this is some of the work that we've done as well, using, for example, some oxide and some foam in a foam material, which has got a very high surface area, and it actually stops the shuttling and it slows down. So it pretty much works like a catalytic material, which actually absorbs it, but also deabsorbs it. So you want the charging and discharging to take place without slowing down one over the other. Yeah, and microstructures are very, very important for that. So you got high surface area. At the same time, you want these materials not to react too strongly with the sulfur and hold them forever. So you need to be released back into the system. I think I'm just going to quickly run through this, and these are all published work from work done in our laboratory, but there are a lot of similar work elsewhere and in other universities in the UK and all over the world. And this is looking at how the capacity in the potential map looks like and how the discharge capacity changes cycle number, depending on the hierarchical structure. So this is kind of fundamental work, trying to figure out what is that combination of ratio of micropores to mesopores to macropores that gives us this best optimization. So this is one of the earlier work. And on the basis of that knowledge, we're able to develop very specific morphology of materials with extremely good performance. So therefore, the fundamental understanding is quite crucial. Yeah, and you can use various kind of conductive materials like graphene and carbon nanotubes, for example. And this here is a few layer graphene foam, and that again you can see is a very, very stable capacity over a cycle number of 400 in the laboratory, and it actually gone up to more than 1,000. So these structures are important to know, but these materials are not available in large quantities at the moment. So of course, in the future, therefore, the potential exists. Our carbon nanotube, they're grown in such a way that they are like forests, and they also serve the same purpose. Therefore, they create that kind of microvoids, and at the same time have allowed the electrolytes to penetrate. But nevertheless, they allow this capacity at the right density of the forest, if you like, and the capacity is high. At the same time, the cycling life is good. Yeah. Okay, I think, yeah, so these are further examples of different morphologies that seem to offer those advantages. Yeah. I think I'm going to say that I think that some of these materials, they are amazingly new materials. Some of you know the 2B materials and nanostructured carbon materials. And other 2D materials like sulfides and oxides. I mean, they are not available in large quantities, but they are a fantastic research tool at the moment to move in this direction. But they offer the morphologies we're looking for. Okay, so I think I want to now say in the next 5-10 minutes, it's important to know the supply of the materials required for these batteries. Yeah, because we know that the brine lakes in high altitudes in South America, Argentina, Bolivia, and Chile, and China in the Tibet area, they have a large amount of lithium, relatively large compared to the oceans, for example, they concentrated lithium. And they produce, Chile is one of the largest producers in the world until recently, about 700,000 tons per year expected from that source. And the price of lithium has fluctuated. Perhaps it's about $17 per kilogram. And it is forecast to come down as more production takes place. And Bolivia has a huge potential to develop in the future. But lithium content in these salt lakes vary from 0.1 to 0.158%. In seawater, it's parts per billion and less. But also from lithium rocks. Yeah, and this is a growing area for battery application. And this, for example, is much richer and it's a large source. Australia, in fact, has become the largest source of lithium at the moment, and is expected to be 1 million tons per year. LCE stands for lithium carbonate equivalent because they're sold normally as lithium carbonate, sometimes a lithium hydroxide. But it's twice the capital cost to unlock this lithium from the rocks, which are silicate rocks. And the salts mostly this is an example of a salt lake. And of course, we know that brine water in Cornwall has lithium from the old mines, and that is being exploited, or work is done on it at the moment to exploit that. And the salt mostly present, as we know, as chlorides, and the typical composition is given here. The lithium to magnesium ratio is very, very important. And these are evaporated away. And they have been in use for ages for potassium, for example, for fertilizer industry, except that lithium has a different solubility from potassium, so therefore it concentrates in the salt. And by addition of lime, one can remove the magnesium, which actually it can otherwise pose a problem, and then get the lithium as lithium carbonate by adding sodium carbonate. So there's a lot of transportation required to those high altitudes with things going up and down, and all kind of raw materials required, like sodium hydroxide and sodium carbonate. Okay, I think this is, I won't spend too much time on it. I think sodium ion and potassium ion batteries in the mix is increasingly becoming important with cost and availability, and is a geographical distribution becomes important driving force here. So I think we know at the moment, if, for example, Faradion, which was developed sodium ion battery in the UK, they licensed the whole technology to Reliance in India for manufacturing in India. So it's, because it seems like it's a good mix for battery development. Okay. So, see, I think when we have 1 kilogram gasoline, it can generate 15 times more energy than 1 kilogram of lithium-based current batteries. Yeah. But that gasoline can never be recycled. But the lithium in principle, and I'm sure in practice, will be recycled. Yeah, especially it will be recycled at low net energy consumption using renewable energy source. And electricity for manufacturing, charging, and recycling, all that coming from renewable sources in the future. Yeah. And if the bill of materials such that it's $100 per kilowatt hour, then EV powertrain net system is comparable to internal combustion engine powertrain. So that's a tipping point, and that tipping point is expected to take place within the next few years. Okay. There are other critical materials as well, as I mentioned lithium, but really the cobalt, vanadium, tin, rare earths, nickel, copper, all these are crucial in the development of this battery technologies in the future. So if you bet on NMC 811, the low cobalt material for the future dominate, and this is the direction in which Europe is going, the demand for nickel, cobalt, lithium will increase in unbelievable quantities from 2019 to 20% electrical vehicle penetration in 2025, assuming in one scenario. That's a very rapid growth. It's from 2.5% now to 40% in 2030. These are massive turnover in a very short time, but there is a possibility this is going to happen. So nickel, you can imagine from 100,000, 46,000 tons, it's going to 3 million tons per year. Cobalt is actually be a bottleneck, to be honest. It's a huge quantity of cobalt required. It can be recycled. Of course, batteries will be available for recycling of cobalt. Nevertheless, because cobalt is available geographically, is distributed only 2 or 3 places in the world. Yeah, and DRC in Africa actually produces 75 to 80% of the cobalt. So it's a very, very supply chain constraint. And cobalt is of importance in other industries as well. And the lithium, if form as small chemical industry, will become a huge tonnage industry. Okay. So yeah, so I think also the number of batteries factories required. Yeah, they require about 60 gigafactories from, I don't know, currently 8 or 15. Some are under development, some are nearly finished. So yeah, so even if it's 15, it's 4 times the number of gigafactories, are large factories, and they'll probably be dominated, I think, by China and EU, given their plans. But innovations, growth taking place all over, including plants appearing in the UK. and 13 have been earmarked in the US to develop very soon. And Japan and South Korea, Taiwan, Singapore, I mean, these are all leading places. And India is also beginning to invest heavily in lithium-ion batteries and sodium-ion batteries. Okay, so yeah, so just the European plan is 250 plus gigawatt 15 to 20 years. That alone will take 50 gigafactories. Okay, I think I sort of in the end of my time now. I think I just wanted to say that for recycling, it's important to look at the existing methods that are green and follow the examples for lithium-ion batteries, because although there are lots of companies are available at the moment to recycle, but they're all early stages, and we just have to see how, because not recycling these batteries, especially large batteries used in electrical vehicles, will not be an option, because it's absolutely be compulsory to recycle. Yeah. So there's some work we did with the lead acid battery, and just because we know that the current method of recycling lead seemed quite polluting, and that produces SO2 fumes and lead fumes and CO2 emissions and lead effluent and lead slag. And it's got capital intensive, requires a lot of energy. And we developed a hydrometallurgical process whose capital cost is 1/4, and is actually consumption of energy. It's actually nearly net zero energy. It's carbon neutral, no lead fumes, no SO2, because there's no high temperature process where lead can boil. And in fact, extra energy is available for refining the grid alloys. And it's a very simple method of using a waste battery, leaching it with materials which are biofuels, essentially, and they produce crystalline compounds which burns by itself at a very low temperature, about 300 degrees centigrade, produces a lead oxide precursor, which can be converted into new batteries straight away. Yeah, and enough energy is available from the combustion to refine the grid, the current collectors. And this is just an example of the various structures we produce in that process. And the heat generated from the combustion, it just ignites by itself. It's the source of energy. And the structure that you finally produce, it is, you can see that it is nanocrystalline grains joined together like coffee granules. So therefore, they're very easy to transport. It doesn't fly about. Yeah, so they're just agglomerated, but with a large surface area available from the nanocrystallites. And there's some examples of further examples of the structure after combustion calcination, as we call it. Yeah, and this has been licensed to a US Swiss company, and there's a company in the UK near Birmingham who actually have a pilot plant for this. Yeah, in fact, because of the nanostructuring, there's 30% greater energy density in this material compared to the normal conventional materials. Yeah. And the battery life seems to increase as well. So this also improves the battery tremendously. So therefore, it's not recycling, which is green. It actually produces a product which is much better. Okay, I think, yeah, so I think that's mainly what I wanted to say. And I think I just put this here. Umicore is one company in Europe which actually recycles the lithium-ion batteries at the moment using the smelters, but they recycle a lot of other things in those factories, electronic PCBs, etc. And they rely on expensive byproducts like platinum and gold and silver and cobalt for running these processes, but they use some hydrometallurgical process for refining. So such a process exists, but I think we have to develop some other methods for dealing with large quantities in the future. There are many opportunities here. And this is just Eversource is a company which is actually developing some new technologies, because they already have a lead acid recycling pilot plant. They want to use similar ideas for lithium-ion batteries as well. I think that, yeah, thank you very much for your attention. I'd like to thank many of my research colleagues, PhD students and research associates and technical staff industrial partners and collaborators from all over the world for carrying out this amazing, interesting phase of research in batteries. Thank you very much for your attention.